Okay, here we're going to look at the actual functioning of a buffer by comparing the pH that would have resulted if 20 milliliters of 0.2 molar HCl was added to 50 milliliters of water, or if it was added to 50 milliliters of this buffer solution. Excuse me. So, if 0.2 molar HCl was added to 50 milliliters of water, 20 milliliters of it, then we basically need to figure out how it got diluted to figure out what the new concentration of HCl is, and as a result, what concentration of H3O plus will be made. It's a strong acid, so all we have to do is change the concentration. So C equals N over V, N equals CV. So by diluting it, the number of moles won't change. So the first thing I'm going to do is calculate the number of moles. And then, taking into account the addition of the 50 milliliters, the new volume of the solution will be 70 milliliters. So my new volume is 0.07. So my concentration, which is N over V, will be 0.04 divided by 0.007. And I'll get not 007, just 07. A new concentration of 0.057. HCl is a strong acid, so I don't have to worry about any equilibrium stuff. I can assume that it all goes into creating hydronium. So if I have 0.057 molar HCl, I have 0.057 molar H3O plus. So I can do my pH directly then. And I get 1.24. So if I added 20 milliliters of my 0.2 molar HCl into pure water, I would get, my pH would drop to 1.24. Now let's look what happens if I add the same thing into my buffering solution. So here I'm going to have my HCl going into my buffer, and my buffer contains HF and F minus. This is an acid, this is a base, the conjugate. So this being an acid will react with the base, F minus, to produce some more HF and some Cl minus, which doesn't matter, that's not going to do anything. So if I have 20 milliliters of 0.02 molar HCl, so C equals 0.2, and I have a volume of 0.02, I'm going to get 0.04 mole, or 0.004 moles of that. We can see that calculation right here. And I have a 50 milliliter 0.2 molar solution of F minus. So volume is 0.05, concentration is 0.2, so N equals CV equals a concentration of 0.01. They're not a concentration, number of moles of 0.01. So this will be my limiting reagent. This will react away completely, producing 0.004 moles of that, and leaving 0.006 moles of that. Now to figure out what's actually going to happen to this equilibrium situation is a little bit tricky. We need to remember that because this is a buffer, it contained both HF and NAF before. So I need to figure out how much HF was, right now I'm down to 0.006 moles of F minus, and I've created 0.004 moles of HF, but I need to figure out what my total amount of moles was. So I have new 0.004 moles, but originally unreacted, I had a concentration of 0.2 molar, and I had 50 milliliters. So my original amount of moles, concentration times volume, is 0.2 times 0.05 or 0.01. So I have 0.004 new. Original, I had 0.01 from my buffering. So my total is now 0.014. Also note that my volume is increased to 70 milliliters when I added the 20 milliliter and the 50 milliliter solution together. So now if I want to consider my equilibrium, HF plus H2O going to H3O plus F minus, I can recognize that for F minus, for example, I have 0.006 moles in a volume of 0.07 liters. So I have a concentration in my starting situation of 0.0857. For my HF, I had 0.01 in the original buffer. Through the reaction, I increased it by 0.04, and so my new moles is 0.014 moles. I am in that same volume of 0.07, and so I think it's 0.2 here, yep, 0.02. I have a new concentration of 0.02 molar. Hold on, that doesn't make a lot of sense. 0.2 molar. 0.014 divided by 0.07, yeah, 0.2. You might say to yourself, well, hold on a second. I started with 0.2 and I added some. How did I end up back at 0.2? Well, remember, I added some moles, but I also added some volume. So by adding moles and volume, I ended up back at the same concentration. It's a little bit of a coincidence, but I increased both the number of moles and volume, so it's not surprising that it ended up going back to the same. I can ignore the initial population of my H3O plus so that my change is predictable. I'm going to add X here. Taking X away here. I'm going to recognize that my K for this acid, I want to say, is 6.6 times 10 to the negative 4. Yeah. So these changes are all going to be small. Or you could look at it as a common ion situation, but if I take the concentration 0.2 divided by my K, it's much greater than 100. So this 0.2 minus X is going to be approximately equal to 0.2. X and this in this 0.0857 plus X, this X is also going to be small, so that's just going to be approximately 0.0857. So my K expression here for my acid is H3O plus F minus HF, and that's my Ka, 6.6 times 10 to the negative 4. And this is X, and this is 0.0857, and this is 0.2. So 6.6 negative 4 times 0.2 divided by 0.0857, and I get 1.5 times 10 to the negative 3. So this is good, and this is still okay. This would have been with the addition, would go up to 0.087 or so if I added the 0.15 in, 72, and that's close enough to 0.857 for my calculation here. So both of those assumptions are okay. So the concentration of H3O plus is equal to 1.5 times 10 to the negative 3, and I can do the pH of that. And that's 2.8. So with no buffer, adding the acid to the water dropped the pH all the way down to 1.24. By having the buffer, the pH was only dropped to 2.8. Those numbers aren't that different, but remember the pH scale is a logarithmic scale. For every 1 on the pH scale, you're talking about a factor of 10. So 2.8 is a lot less acidic than 1.24. Is it 1.24? And so we can see that the existence of the buffer prevented the HCl from making this into a strong acid. Instead, it reacted with the HCl, leaving behind only weak species, and as a result, not as much of a pH change or not as much hydronium or hydroxide in solution. So that's the mathematics of how a buffer works.